Record to this computer. Today we're going to take a look at recursion. Recursion comes up in 161. Recursion comes up in 162 and even in 230 a little bit. So you get a dose here, a dose there. But this one gets you ready for quickly doing the one in 161. All of a sudden it's like, well, this program you can write this method recursively and you're going, oh, we did have this in 161. We're ready to go. Anyhow, I'm going to give you a function. In the math world, you hated these functions. This is called a piecewise function. Whenever x is less than 3, it's this graph. You know, if I was actually graphing it as a piece function, I'd go 1, 2, 3. At 3, I'd be up at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It would be an open circle, and it would come down to something like this, and then go back up and on and on and on. And then the next step. So when I teach piecewise functions in a classroom, I actually give the graph first. You know, this is x squared shifted up 1. And so, yeah. But we're looking at this similarly, but yet a little bit different. So whenever x is less than 3, it would be this guy. I would perform this, y equals x squared plus 1. Graphically, it would look like that. But when we come to recursion, we're going to do something different. We're going to do 2 times, and we're actually going to call the function again. And this is going to be when we have x is equal to 3 all the way up until 5. And then finally, f of x minus 1 plus 6 for when x is greater than or equal to 5. So we can't really think of this graphically anymore, but we're going to use something that here's the domain kind of deal, and then here's what we do depending on that domain value. Okay, so question is going to be calculate f of 8. And how do we do f of 8? Well, let's see. F of 8 is going to equal this domain. It's going to equal f of 7 minus 6. It's going to equal f of 7 minus 6. Well, guess what I have to go do now? I have to calculate f of 7. F of,
Professor,
yep,
Persian kind of like sigma notation mixed with piecewise functions.
sigma notation. Haven't seen that.
The way it works, I mean, the way my brain's processing it is so for f of 7, you have to therefore add it in and you keep cycling and looping like you would in sigma notation for n equals 1 to
Right,
5.
right. But with this one, it's going to be different because once I get to this guy is known as the base case. Once I solve that, I have to re-twirl myself back out of there to all the way back to f of 8. So I'm going down a rabbit hole, and then I have to come back up out. F of 7, that's going to equal f of 6
Fuck yourself. Sorry. Cat.
plus 6. Sorry, I wrote that as minus. It's actually plus 6. Now I need f of 6. It still falls in this category. That's going to be f of 5 plus 6. Boy, now I need f of 5. Ooh, no, it's still there. That equals f of 4 plus 6. What is f of 4? According to this, it becomes 2 times f of 3 plus 3. Well, I guess I have to go figure f of 3. That's going to be 2 times f of 2 plus 3. Now I need f of 2. Yay! What's f of 2? Chinga, 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 chinga.
That would be 5.
F of 2 is 5. So now I can spiral back out. This now becomes 2 times 5 plus 3 is 13. Now I know what f of 3 is. 2 times 13 plus 3 is 31. Now I know what f of 4 is. 31 plus 6 is 37. 37 plus 6 is 43. 43 plus 6 is 49. 49 plus 6 is 55. All right, let me go back in and check. 2 times 5, and that's 13. And well, you did not, you big dummy. That's 29. Nobody caught me, did they?
I was just thinking about I took the Fibonacci sequence program and changed
Yeah.
10 to 100, and then my fans really started spinning up, so I killed the program.
Oh my, 35 and 6 is 41. 41 and 6 is 47. 47 and 6 is 53. That's like the very first time you take Calc 1 and the prof fills the whole first board and keeps going and gets to the second board, says, oh no, I made a mistake over there. Squish, 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 and it goes all the way back to where they started.
Isn't f of 5, shouldn't that be the 2f x minus 1 plus 3 instead of f of 4 plus 6? Oh, yeah,
Yeah, this is greater than or equal to 5.
I wrote it wrong.
Yeah, okay. No problem. First time doing it. You're allowed to
How
screw up
dare you?
when it's the first time. I know.
How dare you?
Look at that mess. Look at that mess. Okay, so recursion. As you know, a recursive function is one that calls itself. Yeah, I don't know. We can see lots of different ones. Code listing 20.2. Somebody's backing up the truck. 20, code listing 20.2. 20.3. That's close. 20.2. Good job, buddy. We have a function called message. Okay. Inside of message, you see if times is greater than 0, I recall message again and again and again. And just like we kind of did, once it gets to a terminal spot, it comes back. But in this case, it just goes 5, 4, 3, 2, 1, 0. And then you see it's returning back. So it's coming in here, calling this when it's done. It does this message and then goes back. So that's why message returning. And you'll see some of this in error messages in Java, how it'll go method, 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 method. Here's where their error was and the path that was used to call it. 20-3. Well, let's see. I'm having my notes. Problem it can solve with recursion if it can be broken down into smaller pieces that are identical. And this is a note. Anything you can do recursively, you can do with a loop, but the recursion can be simpler. The recursion can also be less efficient. Excuse me, the loop is going to be less efficient. Again, the code listings, you had 5 of them. Everybody, I think, got them done. Have to double check on that. 20-3, we have factorial. It's like the biggest, most common one. In factorial, you have the two biggies, the base case, which kind of ends it, and the recursive case. In this example that we just did, we actually have 2 recursive cases. 2 different situations that'll call the function again. Instead of f, we're calling it factorial. but the base case will stop me from spiraling down and help me come on out. 4 factorial. Did you see on Facebook they're now doing the you know how they do the problems 4 times 2 minus 6 times 0 plus 4 and they sneak the factorial sign in. They're trying to mess you up with the order of operations. So now the trick is to do the factorial.
I've seen one of those with the double factorial.
I never heard of a double factorial.
They just put 2 exclamation points next to each other. I don't even know if it's really a thing.
Yeah, maybe.
What's order there? I don't know. Do you solve for the first one and then run it again with the second number?
With the result, I think it would grow pretty fast.
Probably.
Probably
It's,
factorially.
it's like a heavy kid.
Number of characters. Oh, this is like writing dot length. This goes through. There's a base case. You need a base case to make that thing end. And over here we have 2 different recursive cases. Yeah. Different things going on. 25, another one. The greatest. This is a good program. Mathematically, you probably saw it somewhere. What the heck? You probably saw it somewhere. This way of finding the greatest common denominator. Up here is what it's called. The Euclidean method. The Euclidean method makes it kind of nice. And that's a good problem. You typed it in. Hopefully you looked at it after you typed it in and didn't just go, oh, okay, yeah, looks good. Yep. 26. 26 was another one you did. Here is my recursive. This is a little bit like we just did. Here's a recursive. Here's 2 base cases. Getting the old, does the Fibonacci sequence start with 1 and 1 or 0 and 1? Filling those up. This example, it says 0 and 1. But you notice how it keeps calling it the sum of the previous 2 numbers.
Yeah, this one would just keep going if the limiter wasn't the for loop, right?
Yes.
Yeah.
Yep.
That'll make your fans start really moving. Would it be a factorial application there as far or exponential? Like how many times it's running that based on each number cascading down because it runs twice per. I just didn't look at it that one specifically for very long.
Would be 2 to the whatever power because you are calling it twice to get the previous numbers.
Right. So if you're at say 85, then
Yeah. So, you're going to input a number of how many you want to find. And if you mess with this 10, you could quickly get data out of range. Even though
got it.
inks go pretty far.
Oh, when you're moving that high and it's a sequence
Yep.
like that.
Yep.
Right. No,
Like
that
I
makes
said,
sense.
back in the old days in Pascal and so forth, it was this up to 32,767. Does anybody know why?
I can't remember what power of 2 that is, but
Yeah, 64,000. That's 2 to the something power.
is it 16th?
So if it's 16, how many bytes would it use?
Right.
So
Right.
it was old school. It used to just use 2 bytes. Now it's 2 to the 32nd power, cut in half, and that would be the range for integers. Okay. Cool. Let's program. Let's program. What? Where are you? There you are. First one is the problem you did at the beginning of the class. You're going to ask the user for a number. I know a number to pick. 8, because we already did test data. What answer should you get? 53. So you need to create a recursive method for this guy. Yeah, you can call your function f if you want. I don't care. You can call it whatever you want. That's the first one. Looking at them and the solutions are great. Writing it yourself, you got to get in and practice it. Second program, figure out a way to recursively find the sum of the numbers from 1 to n. The sum of the numbers from 1 to n. This was just a side note. A lot of you may already know this formula. Like if I said, what's the sum of the numbers 1 to 10? It's 55. It's 10 times 11 divided by 2. 10 and 2 is 5. It's 55. Where does that come from? The sum of the numbers 1 to n. If I write them in reverse and I add those two rows, each one of these adds up to n plus 1. How many n plus 1s do I have? N. So now I have n plus 1s on the left and 2 times the answer on the right. And when I divide by 2, I get that function. That would have been in pre-calc. You may have seen that for the first time. But these are the two programs I want you to write. The one from the beginning of class, and then I want you to figure out how you can recursively find the sum. So it's this blue part. So let's focus on the two problems. We've already seen a base case and two recursive cases. This is going to take a little more thought. Questions?